Properties of solids is a relatively short topic in AP chemistry. We are now just taking everything we know about bonds and intermolecular forces and classifying the molecules which contain these attractions into multiple and distinct groups. If you haven't yet seen my intermolecular forces video, I recommend watching that before this one. If you're coming from that video, don't worry, this one will be a lot more simple and it's kind of like a recharge. The major thing you need to be able to do in this topic is sort solids into 5 distinct groups. Let's go over each one of these groups now so that you are familiar with their classifications. The first such of these groups that you should be familiar with is called molecular solids. Molecular solids are solids that are held together by weak intermolecular forces, such as London dispersion forces, dipole-dipole interactions, or hydrogen bonds. Examples of molecular solids are ice, dry ice, and iodine. Water molecules are attracted to one another via hydrogen bonds, which I've denoted by this red dashed line here. At room temperature, we know that water is a liquid, but if we get it cold enough, the water will freeze and turn into ice. Because molecular solids are held together by weak intermolecular forces, they commonly need to be very cold in order to actually be solids, such as dry ice, which is just frozen carbon dioxide, but it's been chilled to an extremely low temperature, which is why it's in a solid state. Our next classification of solid is ionic solids. This is when we see our repeating 3D lattice structure, which holds many cations and anions together in a very organized and repeating array. Our ionic solids are really just our salts, such as table salt and potassium nitrate, just to name a few examples. But again, any solid which has this repeating array of anion, cation, anion, cation is going to be an ionic solid, so make sure you're familiar with that. Metallic solids are metal cations in a lattice structure with a sea of delocalized and free-flowing valence electrons. Which just means that, let's say we had all these metal atoms near one another, our valence electrons would be able to flow wherever they please throughout this entire array. That's what we mean by a sea of delocalized electrons, and it's why metal has its properties. The first two groups of the periodic table are technically metals, but they do not form this sea of electrons. When we talk about metallic solids, we are purely referencing atoms that will come together to form the delocalized sea of free-flowing electrons that I just drew. So iron, aluminum, gold, that'll all have those properties. But other metals such as potassium, sodium, magnesium, they will not do that. So they are not metallic solids. Lastly, we have covalent network solids. These are atoms held together by very strong covalent bonds in a continuous network. Essentially, these atoms form one large molecule instead of many smaller molecules, which explains their strength. Examples of this include diamonds, silicone, and quartz. And as you can see here from these images, this is what we're referring to with our covalent network. All these atoms are bonded to each other in a very neat network. It's extremely organized, and that's why it's strong. Now that you're aware of each one of these groups, the other thing you need to be able to do, and the last part of this video, is to infer the properties of each solid based on the forces holding it together. Simply put, we're just going to look at what forces of attraction a solid has, and then we're going to infer the properties of this solid. Chemistry becomes a whole lot easier if we don't try to memorize all the different rules or properties of substances, but rather we just think critically about how different properties will result in other properties occurring. For instance, we know that molecular solids contain weak intermolecular forces. It does not take a whole lot of energy to overcome these forces, and so molecular solids have low melting and boiling points. What else could we infer? Well, because they have weak intermolecular forces, we can assume that molecular solids are going to be very soft as solids. Again, the forces of attraction holding their molecules together are simply not strong enough to result in a rigid solid. Remember that our ionic solids are held together by very strong electrostatic forces. That's an important distinction to make. Ionic solids do not contain intermolecular forces of attraction, they contain electrostatic forces. Because remember, we're making those ionic bonds in our 3D lattice array. Because these forces are strong, we know that ionic solids will have a high melting point and a high boiling point. And again, that's just using some critical thinking. If I have to overcome a very strong bond, I'm going to have to put in a lot of energy to break that bond. Metallic solids have that sea of free-flowing electrons. This results in their malleability and ductility, which again is just another way of saying they're quite soft. We can shape them quite easily. And lastly, we have our covalent network solids. These are the strongest of the strong. They are held together by very powerful electrostatic attractions. and you've probably experienced this in the strength of a diamond. As you might know, we coat the end of drill tips with diamond because it just refuses to break, and so it's the best way to mine through really tough rock. As you can probably infer from our very strong electrostatic attractions, covalent network solids are going to have very high melting and boiling points, and they're going to be extremely hard. And with that, that's absolutely everything you need to know about properties of solids in chemistry. If you're looking for further information on any of the bonds or intermolecular forces discussed in this video, you can find in-depth videos on all of these forces and substances on my channel. If you found any of this confusing, I recommend rewatching parts of the video. If it's still not making sense, take a break and come back later. Thank you for watching.